Good day to you. This is Anagalactic bringing you a presentation in geometry. The audience intended for this lecture is anyone high school age or less if you are interested in getting the correct orientation to the universe in terms of where you are. No mathematics. Mathematics is very important, but mathematics unfortunately has been abused, and now physics is suffering because of a lack of geometry. So if you are in high school, or indeed before, I believe any age down to the third grade, it really depends on you, your interest level, but not on your aptitude. This is a self-contained lecture for anyone. The people that I am not particularly trying to reach are PhDs in mathematics who are probably beyond reach. You will be biased against this because it's a better system than the one that you're in love with. But if you do have an open mind, as I hope you do, you too are welcome to tune in and listen to this broadcast series. This will run until summer solstice, but each one of my lectures is self-contained, and this one in particular is meant to outline everything that I've discovered in the past year for a geometry that has never been attempted. To begin, what we're going to do is reconstruct universal space. Now, the term space has several meanings, and in geometry it's considered to be an abstract term. What we're going to do is construct space first to create linear space. This is the space that has been used for 2,000 years to round it off, and it's currently used at all upper echelon levels of physics, astronomy, and quantum mechanics. Everything in science is linear. That's extremely important to realize, and if you don't fully agree, you need to leave a comment so I can address that directly. Eventually, I'll have a way for you to get in touch with me directly by email, but for now, you don't need to worry. Any questions that you have can and will be answered, but this will be self-contained and anybody can follow along with this. Again, you do not need mathematics at all. The geometry that we're going to construct is one of the two geometries that exist in the universe. It's rather peculiar, from my point of view, to have to put it truthfully, that only one algebra and only one geometry has ever been used by science. It is called linear algebra, and the geometry that is necessarily associated with that algebra is linear geometry. Linear geometry came first. It took 2,000 years and only was accomplished in my lifetime to prove that linear algebra is exactly the line. This is an identification of a geometric object called the line, the straight line, with a number system. The numbers that you were taught in school. These are the numbers that are used exclusively throughout science and always have been. There have never been any other numbers. There has never been any other geometry. But there have been other algebras. An algebra is something we don't need to define here. But if you're curious what is meant by algebra, it's mathematics with variables. There's an anecdote that's been told about Einstein. I'm not sure how much credit one can put to this, but it has been said, and I've seen this in writing, that Albert Einstein had trouble with algebra at an early age because he didn't really understand the use of letters. These would be like X, Y, or A, B, C. But obviously he got past that, and any of us can do that. We're not going to be using Einsteinian mathematics. That's actually the furthest extent that linear algebra can be applied. It has been miraculous on Earth. For technology, and science currently is identified with technology, I myself am aware that that is a misidentification. And whether or not you agree or you think that's a philosophical issue, the point that I would like to bring home to you as we begin is you do not need mathematics to understand geometry. In fact, the Greeks, such as Pythagoras had no number system. Rudimentary, they didn't really use their number system, and indeed it took 2,500 years before it was proved by John Horton Conway that the number system that's used exclusively for science, that's the only number system that's ever been used, is identical with the line. What I'm going to show you now in our first construction, which is the construction of the line, is that the number system associated with it is very natural, and in fact it is blueprinted into us. What is interesting in terms of how we see, which is really how we interpret the universe directly, is through vision. You could say the senses, but it's really our visual, perceptual, spatial system, an onboard system that's hard-coded into us in the DNA code, which cannot be altered. If, by the way, you have any doubts about the code, the DNA code, it is locked, and species cannot change. There is no such thing as biological evolution. If you are interested in pursuing that truth, and it is the truth, biological evolution was disproved in the 1970s through the work of Watson and Crick and those who followed up, who cracked the DNA code. It is locked. It cannot change, and there's no such thing as beneficial genetic mutation. If you have any doubts about that, because this could affect your career and even your life, if you were to disagree with biological evolution, you will not be able to succeed in the current scientific technocracy. But if you would like to be able to defend a reasonable position, the position of science, read a book by Tom Wolfe. Tom Wolfe is the author of The Electric Kool-Aid Acid Test, which is a journalist's account of the Cultural Revolution in the 60s. He also wrote the book The Right Stuff, and then he wrote a series of other books which were rather popular, and he was a very successful journalistic author. But before he died, in his 80s, within the last decade, he published a book on science, and that is somewhat uncommon for an author to switch to science from his other genre. And that book is called The Kingdom of Speech. The Kingdom of Speech by Tom Wolfe outlines the myth of Darwinism and the fantastically engaging story of how the entire intellectual world was hoodwinked with a pure deception that we're descended from the ecology. Human beings are not descended from the ecology. You may think that's religious. That's your problem. Science doesn't deal with religion, but religion will be forced to deal with science. We're on top. You're in the right place to get the truth. What I do is promulgate, promote, and prove the truth of science in one particular area, heaven, what we call the universe. This is what we want. If you don't want that, you're listening to the wrong guy, you're in the wrong place. But if you are curious about your place in the universe, you need to begin with science, with rational logic, not your feelings. not your feelings at all. Only rational logic. Cold, cruel, and heartless. It's way better than religion. Religion is not affected at all by this. Only in the mind of a rational man does science take the lead to decide what religion can get away with and what it cannot get away with. If you're a religious person, you could be on the right path. I have nothing to say about that, except that there are two paths. The masters of the past, who were considered to be enlightened perhaps, such as Yeshua or the prophet or any number of other people, they were not scientifically oriented. They were not addressing humanity in terms of rational logic, but they overlap. We're superpositional beings. You may have heard the term superposition. I'll be teaching you what that actually means. It's an extraordinary term. There's a superpositional logic now, a little bit different from binary logic. It's the logic that the universe uses. But that's getting ahead of ourselves. What we're going to do now is construct linear space. This is rarely performed at the high school level or beyond. We believe, when I say we, the educational system and those of us who are pretty much forced to accept what the educational system offers us, it is considered that in the current educational system and throughout my lifetime and before that, that the linear algebra system or the linear number system, the system of science, the only system that's ever been used by science, is taught to us correctly in grade school. We're going to start over and show how linear space is actually constructed. Nobody in all of science will disagree with anything that I say. So you can trust this, assuming you trust what I just said. Let's start. The first thing you need to do is realize what you're doing. What we're attempting to do is to create a space. And this space is really just empty space. You might ask, how do we know that we can do that? You don't. This is axiomatic. However, every scientist masters this first. The creation of linear space. Just so you know what this will end up being, it will end up being 3D. What does 3D mean? It means 3 lines. You may have heard of space-time. I'm not trying to talk down to you, but it's important to get back to basics. Do you know what space-time is? It's 4D. That may sound peculiar. Don't 3 lines fill space? Yes. But Albert Einstein added a fourth imaginary axis, which he labeled time. We're going to get to that. It's really incredibly simple how this is constructed. But before we can construct space-time or 3D space or the 2D plane, we need to know about 1D, one line. Empty your mind. In order to have an analogy for what this space is, picture yourself looking up into the night sky and you're trying to see the edge. That is space. It has a peculiar characteristic that you cannot really see the end of space. That's tautological, we all accept that. Now, empty your mind of everything except that space. And space has no characteristics, and this space, for the time being, is between our ears, okay? It's behind our eyes. It's what we can visualize. If you're blind, or you would like to imagine that you are blind, you can still do this. This does not affect, I should say, being blind has no influence on your visual perceptual space that you were born with. You were blueprinted with a hard-coded DNA code that enables you to see linearly. And that's why Albert Einstein's space-time works. And that's why 3D works for us and the 2D plane. What is the straight line? We're just going to draw one in the mind. There it is. You can see it. Now, for geometric presentations, it is customary to present diagrams. And you might think that I'm lazy and not showing you diagrams. That is true, I am lazy. That's why I'm a programmer. I prefer not to do extra work if I can get away with it, but I'll work my you-know-what off to make shortcuts to save myself time in the future. That's called a program. Here, what we're going to be doing is simply starting in the most basic way with a blank slate inside the mind. And now, draw a line. It is important to do this in the mind without diagrams. You don't want to project this. Or I should say, you don't want to be confused with what you might see in a diagram. You just have a line. Now, what can we say about that line? That's really an interesting question. What is a straight line? How do we know that there's such a thing as a straight line? That's axiomatic. We have 2,000 years of history to show that this can be done and that it works. But you do have to accept for now that there is such a thing as a straight line. Now we have one. What can we say about it? It goes to two directions, correct? Let's say the line is right here, and it's going out and out and out. It has two endpoints, but indeed, are they points? Well, we don't even know what a point is yet. So we're just going to say that the line goes to infinity. But now you have to think about that for a moment. Is that one infinity or is it two? We're not going to say precisely yet because we don't have a concept of one or two. What we're going to say is that it goes to this infinity and that infinity. And now we're done with step one. Unless you include step 0, which is to establish a blank page in your mind, a blank space. No characteristics, though, so for all we know, that line may be the only thing in the universe. You know it's not, because how in the world did we draw it? We drew it in the empty space that we made. But that space has no characteristics. But it does now. It has a characteristic called infinity. What we think of as the edge. And now you have to remember looking up into the night sky. So this line really is just a line in that space. We're going to say that it goes to this infinity and that infinity. You, knowing how to count, will be quite comfortable with the additional axiom that this line, which we're saying is straight, because we have very good proof of that, we can accept that, but it goes to two infinities. Now what can we do? Well, we can see that it goes to this infinity and that infinity. That's all we need to do is say that, because now we know that it has a center, correct? This infinity cannot be distinguished from this infinity. Once we have a number system on the line, this is jumping ahead, but to let you know where this is going, we'll be able to show that one of them is negative infinity. That's a convention. It's called a valence. This is a 180-degree valence. And now the center has a plus and a minus. So we could say that this is negative infinity over here, and this is positive infinity over here. We can't do that yet, though, because we don't have numbers. But we do have two directions. So we're just going to say that one is negative and one is positive. I believe you'll be comfortable with that, yes? So now we can use that fact that the two infinities are equally infinite, correct? You can't tell if this infinity is greater than this infinity. So we will assume that they have the same magnitude. The fancy word for, all we need to do is give words to this so we can talk about it. But it does have two of whatever we said. Well, those balance on a very important concept called the Archimedean balance point. And that balance point is the center of the space. But in this case, it's not all of space, it's only the space of the line, which you might think is a queer way to use the word space. Don't worry about it. These are just placeholders in an axiomatic approach to just see what we find from building from a line. So now we know that the line has a center. And now we can do something with that line that's quite interesting. And we can do this in one of two ways. This will actually become significant later. The fact that we can take the next step in one of two ways with an equivalent result. And so we're just going to choose one, and then I'll tell you what the other one is. But the way I did this when I first worked this out in my own mind was to erase the line. But now we have something that we did not have before, a center of space. And now that's all we have. Oh, is it? Is that all we have? No. We had two infinities, but once we erased the line, all we're left with are those two infinities, correct? So now we have a center, and we have 2 points that were just left behind. They're just dangling out there. Well, we're not sure they're points. We're not even sure what we even said. So now I want to do it the other way. You bear in mind that when we erased the line, we lost track of the two infinities. Now go back. We have the line. We have the center of the line. So now we have three things besides the line. We have the Archimedean balance point, which will remain even if we erase the line. But we still have the line, and now we're going to do something bold. Take that line at its Archimedean balance point and turn it. What happens to the two, we'll just say point as a random word to describe the two infinities. What happens to the end points of the line? They move, don't they? Now I want you to continue to rotate it, but as you're rotate it diagonally as well. So if it were, what we're doing is, we were drawing a circle, right? That's drawing a circle on infinity, correct? Okay, let's do that and complete it. And now we have a circle at infinity. Now, spin it perpendicularly. What you'll see is that the circle will begin to fill out, and you will have a sphere. This is if you rotate the line in all directions. It will draw infinity, and that is called spherical infinity. That's the name we're going to give it. And now we can erase the line, because now we have two things left: a center and an edge. That's step 2, depending on how you count your steps. That's something we didn't have before. We have an edge that seems spherical, but that's rather difficult to say since it's unbounded. So now we're going to do something quite extraordinary. But before we do, just remember where we left off, that we have what could be a spherical edge. It's not square, it's not cubical, it's not triangular. It's kind of like a spherical edge. I think that's reasonable. We're still in the hypothesis stage, so it's okay to make statements that you need to prove. So have we proved that space is spherical? Technically not yet, because in geometry, a space must be bounded. It must be bounded. That has been, I'll say, extended in many directions, mostly out of desperation, but we won't have that problem at all. We're going to insist on the rules of geometry, that the space you create, in order to be useful in geometry, must be bounded. Why? Why is that so? Is it so? It's because we cannot see infinity. But infinity is the only thing that we cannot see in space. We can see space in our minds. It just goes out and out and out. We can see it. Imagine looking up into the night sky. Can you see the edge of the universe? No. Well, that's pretty much a good definition of infinite distance. All right. Now we're going to examine what Euclid and his successors for 2,500 years following Euclid, in a progressive discovery of the number system of the line, we now know how that happened. It actually took centuries. You can check the history of mathematics to find out how long it took to get the number system onto the line. Remarkably long time. Euclid had no conception of the number line. And you can check me on that. And whether or not you agree or disagree, it doesn't affect us now. What we're going to do is reconstruct the number line. And eventually you'll see at the end of this that's a redundant term. The number system and the line will turn out to be identical. So, we now have a line with a center. Now you would be tempted to say, as we were all taught in school, that center is 0. How do you know that? Is that a real number? Yes, it is. It is on the line. And in fact, it has to exist. And here's why. What possible use could that line be to us as humans? Do you know? What does the line enable us to do? It enables us to measure linear separation in space. And so the number system is the metric for that. This is basically to take the line and realize that you can divide it up. And if you do, you would have to begin at the center, but historically nobody knew that there was a center, and 0 was discovered quite late. But we're moderns, and so we're just going to jump ahead. It's very tempting to me to go through the entire sequence of how we arrived at 0, but for our purposes, we won't need to do that. We're just going to jump ahead to what is actually known in science, that number is 0. And once you know that the center point on the line, the Archimedean balance point of 1D space is what that's called now, the Archimedean balance point of the line. Let's just refresh ourselves here. If we say that that's 0, which of course we do, that means that plus infinity and negative infinity add to 0. Correct? That has become somewhat of a philosophical point, and so we're going to disregard that and start from the inside out. We want to measure separation so we can measure distance. 1, 2, 3, 4, 5. So what's the first number? It's 1. Now we have 3 numbers. 0, plus 1, and minus 1. Right? And plus 1 and minus 1 add to 0. And now I'm going to make a statement that has profound significance, and I want you to concentrate on what I'm saying now. Add is called an operator. It's an operator. It's actually a function. It's the function of linear separation. Add. You might say, well, that means there must be subtract. That's because someone told you that. It is true if you wish to look at it that way, but subtraction is actually a convention. And you may be remembering because you know that you can use addition to subtract. How do you do that? If you add 1 and negative 1, they add to 0, right? That's the same thing as saying 1 minus 1. Because you're measuring separation, right? And if you go from 0 to 1, that's a separation of 1. But you should say it all the way out. It's a separation of 0 to 1. And the distance from 0 to 1 is a distance of 1. Now, if you start at 0 and go negative from 0 to negative 1, what is that distance? See, you could answer in one of two ways, couldn't you? You could say it's a distance of 1 in the opposite direction. That's the geometrical answer. And that's the best answer. But that's not the way we were taught, and actually, it doesn't matter too much. It's one of two conventions. So, if you have a distance of 2 in the positive direction, I should be doing this, 1, 2, that's a distance from 0 to 2. What if you subtract 3 from that? Obviously, it crosses over 0 and goes to negative 1. But what you've done is, you've gone from 0 to 2, and then you add negative 3. They're the same thing. But my point is, you don't really need subtract. You only need add if you have negative numbers. Now, all of that may sound like overly confusing. I hope it doesn't confuse you. But I did want to bring out a very important point. Pardon the pun. Point. I'm sorry about the word point, but we're getting to the point, yes. You're measuring linear separation. Did anything go off the line? No. No, it stayed on the line. And that's add. What we say, then, in advanced mathematics, believe me, this is advanced mathematics now. It really isn't difficult, is it? But consider the advanced statement that sums up what we just did. We can now say that add, which we call addition, but I call it add. Why? It's 2 less syllables. That's the only difference. But I'm just going to call it add. But if you want to say in your mind addition, that's fine. But that is the operator. We use a plus sign for that. That's the only sign that's needed. You never need the subtract sign. All subtraction can be done purely with addition. A moment's thought will convince you of that, but it's not greatly important. It's just a convention. The reason I bring this out is conventions establish a mode of geometry in your mind. So it can be significant which way you look at something, even though they seem equivalent. That'll become important soon. Now, all of this may be stretching your patience. Don't let it, because it's going to get hot and heavy really fast. And we're at 35 minutes. We're going to close this at 40 minutes and have another lecture after this. I don't like to go over 40 minutes. So, we now have a line with a number system that goes to two infinities. That is linear algebra. And that's all it is. But you know that I've certainly left out a lot. What about 2D, 2 lines? What about 3D, 3 lines? Well, that's all those are extra lines. But there's something very peculiar about making a second line in space. We haven't done that yet. Let's do it now. We have a 0 and we have a line, correct? Very simple. What happens if we draw a second line? Well, you can see the line with its center point, so we start at the center just by convention. We'll say that all lines go through the center. This is, in fact, what has been done. So I'm not making this up. But you might have some questions about that. Is that necessary? Why does the second line have to go through the center? Because it's balanced. And so then you can see that there's a straight line. Think of it as a flat horizon. You're just looking at a line that's horizontal. It's not tilted. But this second line could be tilted, couldn't it? We call that an angle, but we don't want to use that word yet. We don't know what it means. Technically, in an axiomatic approach, we haven't defined what that means. But you can see it. But there is a center. If you have this line that's horizontal, you know where that second line goes. It goes vertical. That's magic. That's magical that exists in space. That is, the way we see enables us to see that those two lines are perpendicular. Not meaning to get spooky or philosophical, but that's actually the only reason that we're able to construct linear space to compose the universal space that science uses. It's because of what is called perpendicularity, but then later on you learn the more big boy term, it's synonymous, orthogonality, orthogonal. These two lines are orthogonal. That's magic. Because you're making proportional space. You have 4 quadrants now that are 4 squares that go to infinity. And now we need depth, because that's flatland. And there's a book by a man named Abbott that's gone into over 30 reprints. It's just a marvelously juvenile, delinquent book. Very misleading. I don't like that book. It is beloved by geometers, but that's because of what you're going to find out from my discoveries. But it is the way science works. So it is remarkable that we can have a 2D flat space called a plane. Right? All of this is familiar. And now you know what's next. If you take that plane, which could be like a window between us, right? So it's you and I, for instance, would be looking through it at on a perpendicular line through the plane. That's axis 3. And the first one that we made, the first line is x. And the vertical one is called y. And the third one that goes this way in and out, that's called z. Z. Not z. If you say z, you're fine as long as you're in America. And even if you're not in America, everyone will put up with you. but the rest of the world calls that letter Z. Just so you know. X, Y, Z. And that's 40 minutes. We just constructed linear space. In the next lecture, we're going to very briefly cover how Albert Einstein added a fourth perpendicular line. You may object to that. Stay tuned. I will disambiguate that and make you just as smart as Albert Einstein was in this respect. Don't expect to catch up with Albert Einstein overnight. But using geometry, you'll not only catch up with him, you're going to pass him. This is Anagalactic. We'll be right back. Stay tuned for the next lecture. You won't want to miss it, because we're going to build spherical space. It's my discovery, 2022, a number system for spherical space.